So analyzing collisions in 2D is basically analyzing collisions in 1D, just doing it twice or just doing it simultaneously, right? And there's a nice popular example, billiard table, and that's the example I have below. But just as a general strategy when you're doing these, as I mentioned, analyze each dimension independently, right? And it doesn't have to be the standard, X and Y like that. Just like with dynamics problems, you can angle your axes if you want for some reason. Any way that you want that kind of helps you get the solution more quickly or in a way that you're comfortable with. When you're looking at each dimension, though, remember momentum is always conserved, right, in every dimension. So whatever the momentum before is in the x direction, that's the momentum after in the x direction, even if it's zero. If it happens to be an elastic collision, then you also have the fact that kinetic energy is conserved, and you can use any of those final velocity equations that we found earlier. So for this example, we have a billiard ball traveling 2 meters per second north, strikes two other stationary billiard balls in an elastic collision. One ball ends up with a velocity of 1.4 meters per second, east 60 degrees north, the other 0.4 meters per second west. And we want the final velocity of the first billiard ball. So one thing I wrote down here, well, first a coordinate system. So I'm going to say north is positive y, east is positive x, as is probably commonly the case. The other, I know billiard balls aren't always exactly the same, particularly if it's the cue ball, it's a little more massive, but we'll just say all their masses are equal, particularly since nothing's given here. And that'll simplify our analysis a little bit. So as always, I like to do a sketch to sort of see what this looks like and also to help appreciate my final answer. And so that's what I've got here, right? I've got V initial of ball 1. That's what I tried to write in here, just so you know that's like a 1 down there. And that's 2 meters per second in the north direction, right? And then that hits ball 2 and 3, and we were given those velocities. Ball 2 has that velocity of 1.4 meters per second, 60 degrees, or east 60 degrees north. And the other ball, which I'll call ball 3, has a final velocity of 0.4 meters per second directly west, right? So you can kind of appreciate where these other two balls go. What's the final velocity of ball 1, right? And you can maybe appreciate maybe somewhere kind of in between them. Hard to say exactly, but so what I did here and here is I just said, I know that angle is 60 degrees, right? It was reported as east 60 degrees north, so that's the way I drew it. And as always, if you need to, start with the actual angle. So actually say, like, well, if I want this side here, I know the sine of 60 degrees equals whatever that side is, let's just call it y for now, divided by the hypotenuse of this triangle, 1.4, and then rearrange that, and that's exactly what I have there. So I'm just back, saving a little bit of work and putting those numbers right on there. So now I can look at each dimension independently. So I looked at the x direction first, and the momentum before I wrote is 0. That's because this billiard ball here is going directly north, so 0 velocity in the x direction initially, which means the momentum in the x direction is 0, right? And that has to equal, I just wrote m, like I said, for all the masses. So the first one, v final of 1 in the x direction plus v final 2 in the x direction plus the momentum of billiard ball 3 in the x direction. And then I just sort of put in some numbers for those. Like I said, for v2 we know that's this here. And for the third one, note that that is negative, right? The 0.4 is in the negative direction, so that's what I wrote there. And from there, it's just solving that actual equation, right? V final of ball 1 is what I want in the x direction. Sine 60 is a half. So I'd get the 0.7 minus 0.4 is 0.3. Subtract that from both sides or take it to the other side. It becomes negative. And that gives me the final velocity of ball 1 in the x direction. And then I can turn all my attention to the y direction and only look at that. In this case, before, I have this velocity is in the positive y direction. So again, I'm just writing all the masses as m, and that velocity is positive 2. And then I've got, that has to equal the final velocity after, so that's the momentum of billiard ball 1 after in the y direction. And then I've got the momentum of billiard ball 2 in the y direction, which is that term there. So the mass times that velocity. And for billiard ball 3, it's only moving in the x direction, so that's going to be 0. So I wrote in the 0 here. And then once again, I didn't actually show this in the last one, but because I've got an m in every one of these, right, they do just cancel out. Although that whole term's 0, so it doesn't really matter. And that was the same thing up here if you were following that, right? I had an m in every one, so they just divide through by m, everything cancels. So I have the same thing again here, which just leaves me with 2 on the left side equals v final of billiard ball 1 in the y direction times 1.4. The sine of 60 is root 3 over 2. That's why I wrote that. And then I just made this a decimal, subtracted it from both sides, and that gives me my answer. And now, just like in a dynamics or kinematics problem, I now have the two components. I know the v final of billiard ball 1 in the x dimension direction is negative 3 or 0.3 meters per second, and now I know y. So I can say, well, that looks basically like this, right? Because the 0.3 was negative and 0.78 roughly 2.5 times that. So I would sketch something like this. Also note, like, I put the angle here, and always just be aware when you draw your angle. I even made it an arrow because I just want to be aware I'm going from west toward north. So when I get that angle, that's the way I'm going to report it. To calculate the magnitude of v final of ball 1, it's good old Pythagoras. We know it, we love it, we've seen it many times. Square the numbers, add them, square root, you get it. This here, I just wrote it that way, sort of the way I did before. I said I have this angle here, and I have the opposite side and the adjacent side, so that means the tangent of theta is going to be 0.7876 over 0.3. And then that means you can actually put this into a calculator. Just make sure you're doing the inverse tangent of that to get theta. And when you do that, also make sure that sort of matches up with what you know, in case you ever accidentally have your calculator in radians or something, or punch it in wrong. I get 69 degrees, and that, like I said, that sort of makes sense given the sides I have of this triangle. And so then I can make my statement. That means v final 1 is 0.8 meters per second west, 69 degrees north. And again, just double checking that's the way I drew it.